Hello, welcome to Biochem series. In this video, I will take you through energy balance. Please, if this is your first time of visiting my channel, kindly support me by subscribing. And also, if you are a return viewer who haven't subscribed to my channel yet, kindly support me by subscribing as well. Thank you very much, and I appreciate all your support and help towards the growth of my channel. So this particular video is a full tutorial about energy balance. I am going to start by talking about the general concept of energy balance, and then I'll move on to talk about the general concept of heat balance, then talk about heat exchangers as well as how we perform heat balance calculations with some trial questions and then worked examples. So please watch the video from the beginning to the end so that you won't miss out anything. Thank you very much. Now let's start. So from our basic understanding of energy, we know energy to be the capacity to do work or the ability to do work, and the units of energy are joule or kilocalories. So kilocalories is normally used by the nutritionists and then the dietitians. So energy can take different forms. We have the potential energy, the kinetic energy, the heat energy, chemical energy, electrical energy, and then many other forms of energy. So let's move on to talk about what you call the law of conservation of energy. The law of conservation of energy. This law states that energy can neither be created nor destroyed, but can be transformed from one form to another. So for us to appreciate this particular law very well, let's recall mass balance. When we were doing mass balance, we came to understand that for any system that is in operation, the sum of masses of anything entering the system should be equal to the sum of masses of anything exiting the system. In other words, mass is conserved. That is, mass in is always equal to mass out. We don't create masses or we don't destroy masses. Likewise for energy as well, we don't destroy or create energy. When a particular system is in operation, energies are not destroyed or energies are not created within the system, but we rather transform one form of energy to another form of energy. So for instance, when you have a particular plant that is working, mechanical energy can be used, or like mechanical energy can be converted into heat energy through friction. But we can't destroy the mechanical energy and then create heat energy. It's like we are not destroying one form of energy and then creating another form, but we are rather converting one form of energy to another form of energy. So let's keep this in mind that when a particular system is in operation, we have many forms of energy at work. We can have electrical energy, heat energy, light energy, kinetic energy, potential energy, and then many other forms of energy all at work in the system. But we don't create any form of energy or we don't destroy any form of energy. We rather do interconversion of energies from one form to another. So we can perform balances on energy as well. As we were able to perform balances on masses, we can also be able to perform balances on energy. But due to the problem of interconversion of energy from one form to another, it becomes very difficult for you to isolate a particular form of energy and then perform balance on that energy alone. So for instance, when we have kinetic energy, potential energy, heat and the light energy at work in a particular system, it will be very difficult for you to isolate, let's say, light energy alone and then perform balance on it, isolate electrical energy alone and perform balance on it, or isolate, let's say, heat energy and then perform balance on it. It is very difficult. So what we do is that we focus on the predominant form of energy in the system and then perform balance on that particular form of energy. It's not like that form of energy is the only energy in the system. We understand that there are different forms of energy in the system, but due to complexities in performing energy balance, we focus on only the predominant form of energy in the system and then use it for the calculation. So we perform balances on the predominant form of energy in the system and then ignore the other forms of energy in the system. Energy balance is just an attempt to balance the energies entering the system and then exiting the system. So energy input, that is energies entering the system, should be equal to energies output. That is energies exiting the system. So our energy input, that's the energy in, can be in a form of direct energy or indirect energy. So direct energies are those forms of energies like fuel or like electricity that we use to power the industrial plants. So when you go to the industry, some of the machines there run on diesels or petrols. So these energies that we burn, or these energies stored in the fuels that we burn to power the plants, can be considered as direct source of energy. And also some industrial plants rely on electricity. So the electricity that we use to power the industrial plants can be considered as direct source of energy input or like into the system. We can also have what you call the indirect sources of energy or like indirect energies input. So for the indirect energies input, these energies are not directly associated with the system, but they are those energies that, for instance, we use to build the industrial machines. So when you go to the industries, those plants that you see there, those industrial plants that you see there, we use a particular energy to build those machines. So the energy that we used in building those machines can be considered as indirect source of energy input. We can also consider energies that we use to generate electricity. For instance, when you go to those hydroelectric power stations, those energies that we use to turn the turbines in order to generate electricity can all be considered as indirect sources of what energy input into the system. And also we can talk about the energies that we used in refining the crude oil to obtain our diesel that we use to power the industrial plant. All these things, as well as the energies that we use to transport our raw material from the farm to the industry. So we can consider all these things as indirect sources of energy. So as this particular formula goes, total energies input should be equal to total energies output. Energies coming into the system should be equal to energies exiting the system. So that is how energy balance also works. It is like the mass balance. Mass in is equal to mass out. So here, energy in is equal to energy out. So let's talk about the basis of energy balance calculation. What at all do we base on to do our calculation? That is what we are going to do. So if we can recall from mass balance, we came to understand that when we are performing mass balance, we can consider whatever is entering the system and then whatever exiting the system to write our balance equations. And at the same time, we consider what we call the component balance. And we said that component balance is the balance that we write with respect to a particular component. So we can say that we can base on a particular component to write mass balance equations. So ask yourself, if you want to perform calculations on energy balance, then what should we base on to do the calculation? So we can base on what you call external energy per kilogram of a product. We can base on the external energy that we used to produce a kilogram of a product and then perform balance on that. We can perform the balance by basing on the external energy that we use to produce a kilo of a product. Most of the times, the question will come in such a way that the energy that we use to obtain, our products, like the question will give us the total energy that we use to obtain our final products, but it won't let you know the energy that we use per a kilogram of a product. So in those situations, what you have to do is that just divide the total energy that we use to produce the product by the flow rate of the product, and that will give you the energy used per kilogram of a product. So you can use that to perform your calculation. Likewise, we can base on what you call external energy used per kilogram of raw material. That is, we can perform the calculation by basing on the external energy that we use to process a particular raw material to give us that particular final product. So there's here too, when the question didn't talk about, the external energy used per kilogram of product, then you have to divide the energy given to you by the flow rate of the feed in order to, get your external energy used per kilogram of raw material. But in most cases, they give you the figures that have already been converted. So the only situation whereby you have to do the division is when you are giving the flow rate of your raw material. So please take very good note of that. When you come across a question whereby you are giving the energy that we use to process a particular raw material, or the energy that we use in obtaining a particular product, and you are at the same time giving flow rate of your feed or a flow rate of your product, just do the division, divide that particular value you were given by the flow rate in order to get the energy per unit, or like per kilogram of a raw material, or per kilogram of a product. When we start doing the calculations, you'll be able to appreciate what I'm talking about very well. So this is basically what you have to know about energy balance. So let's continue with heat balance. So as I said, in a given system, due to interconversion of energy, it becomes very difficult for us to isolate each of the forms of energy and then perform balance on them. So we focus on the predominant form of energy and then perform balance on that particular form of energy. So when you consider a particular system at work, the most common important form of energy in the system is heat energy. Let's consider a scenario like this. When you have raw milk and then you want to pasteurize that particular milk, the form of energy that we use in the pasteurization process is heat energy. Also, when you have, let's say, fresh tomato and then you want to concentrate the tomato into final products, the form of energy that we use in the evaporator in concentrating the tomato by removing water from it is also heat energy. There are many instances in the industry whereby heat energy predominates the system. So that is why it is very advisable for us to learn about heat balance and then learn about how some calculations on heat balance are performed. So we are not limited. It's not like heat is the only form of energy in the system, but since heat mostly predominates the industrial processes, then it is good for us to learn heat balance and then understand how calculations are performed. So for heat balance, it will work in a similar way as that of energy balance. So heat in is equal to heat out. Whatever heat entering the system should be equal to whatever heat exiting the system. So this particular diagram gives a broader view of heat balance. So we can see that the heat in can be the heat that comes from the electricity source, or the heat that comes from combustion of the fuel, or the heat that comes from other mechanical sources. And lastly, we can talk about the heat that comes from the raw material. The raw material in itself might possess certain heat already. That is why it was counted as part of the heat in. So we also have another category of heat called the heat stored. So the category of heat that we call the heat stored can be the heat coming from the surrounding as well as the heat going into the surrounding. So the heat that is coming from the surrounding into the system can be categorized as part of the heat in, whereas the heat that is leaving the system into the surrounding can also be considered as part of the heat coming out of the system. So our heat out can also be found as part of the product, or can also be found as part of our waste material. So all in all, heat in is equal to heat out. Whatever heat entering the system should be equal to whatever heat exiting the system. We have to learn something about what you call sensible heat and then latent heat. So when you consider a particular system at work, anytime there is a heat change in the system, the heat change can be in a form of sensible heat change, or it can be in a form of latent heat change. So we are going to learn about these two forms of heat changes and then learn about how we can use these to perform calculations. So let's start with sensible heat. Sensible from the word sense. That is something that you can feel or sense it. So sensible heat is just a form of heat which, when added or subtracted from material, causes a change in temperature without a change in the state of that particular substance. So for us to appreciate it, let's consider water. Let's say you have water at a temperature of 50 degrees Celsius. When you start boiling the water to a temperature of, let's say, 70 or 80 degrees Celsius, you can feel that there is temperature changes. When you put your hand in that particular water, you can feel that the temperature of the water has increased from, let's say, 50 to 70, but it still remains in the liquid state. That is, in other words, no changes of state, like no change of state of matter has occurred. We are still working, or like we will still be having the liquid water. So the form of heat that changes the temperature of a particular substance without changing the state from one state of matter to another, we call that form of heat sensible heat. So the formula for sensible heat is given as mc change in T, mass multiplying the specific heat capacity and then multiplying the changes in temperature. So all these parameters will be given in the question, and it is just a matter of you fixing them into the formula and then using it to perform the calculation. And the unit for sensible heat is given as joule per kilogram Kelvin. Joule per kilogram Kelvin. Please take good note of the formula. Sometimes I think some questions will ask you that what is the unit for sensible heat. You have to know what to write, and also when you perform calculation, know the final unit that you will write, because units are very important. Let's move on to talk about latent heat. Latent heat is like the reciprocal of sensible heat. Latent heat is just a heat required to change the physical state of materials from, let's say, solid to liquid, or from liquid to gas, or from solid to gas at a constant temperature. So let's consider this scenario. Assuming that you have water that is kept at a temperature of 100 degrees Celsius. Water at 100 degrees Celsius. When the water starts boiling into vapor at 100 degrees Celsius, the form of energy changes. The form of heat energy changes can be considered as latent heat, because you are transitioning from liquid water state towards vapor state. You are moving from liquid state to vapor state. So far as there is phase changes, whilst temperature remain constant, that is, we are still at the 100 degrees Celsius, but we are just having phase change from liquid state to gaseous state. So we call the form of heat changes the latent heat. The form of heat change that is occurring there is called latent heat, and the formula is given as mass multiplying the latent heat. So we have the latent heat of vaporization, we have the latent heat of fusion. All these things are constant. That will be given in the question. The unit is joule per kilogram. So take good note of this. So that is all about latent heat and then sensible heat. Let's consider this particular work example about heat exchangers. So a fresh milk at 4.4 degrees Celsius is being heated in a heat exchanger to 54.4 degrees Celsius by hot water. How much heat is needed for a feed flow of 4536 kilogram per hour, and you are to take the heat capacity of milk to be equal to 3.85 kilojoule per kilogram Kelvin? This is the question. So first of all, ask yourself, am I going to use latent heat formula, or am I going to use sensible heat formula? These kind of questions are very simple. All you have to know is that just try to spot whether there is heat change. Like, just try to spot whether the heat change here is what sensible heat change or latent heat change. So let's start breaking down the question. We can see from here that the fresh milk was initially at 4.4 degrees Celsius and it was heated to 54.4 degrees Celsius. And from the definition of sensible heat, we came to understand that sensible heat will cause changes in temperature without any changes in what phase. So far as temperature change is occurring, it should be able to give us a clue that we are working with what sensible heat. So the heat required should be what, or like the heat needed should be in the form of sensible heat. So let's just quote the formula. But before then, let's fish out the parameters from the question, and then after fishing them from the question, then we fix the parameters into the sensible heat formula and then use it for the calculation. So the question gave us the initial temperature to be 4.4 degrees Celsius. Don't forget that the units for sensible heat the unit for sensible heat has Kelvin in it. So let's try to convert the temperature from degrees Celsius to Kelvin. So when you have your temperature in degrees Celsius and then you want to convert it to Kelvin, it is just a matter of adding 273 to that particular figure. So the T1 will be equal to 277.4 Kelvin, and then the T2 will be equal to 327.4 Kelvin. And also the question gave us the mass flow rate, that is the M. The mass flow rate was also given as 4536 kilogram per hour. 3 says kilogram per hour. Ideally, we should have had this particular value in seconds. We should have had this particular value in seconds. So you can choose to divide this particular value by 3,600 to obtain your mass flow rate in the form of kilogram per second. You can do it directly, or you can finish the calculation and then you do the division to have your final value. So we are also having the heat capacity of milk, that is the C, to be equal to 3.85 kilojoule per kilogram Kelvin. So we can now fix all these into the formula, because you see the heat required is the same as the sensible heat change. It's the same as the sensible heat change. So let's start fixing these values into the sensible heat formula. So we are going to have 4536 times 3.85 and all multiplying the changes in temperature. That is 327.4 minus 277.4. I intentionally added the units of each of them. I don't want you to be confused. That is why when I wrote the mass flow rate here, I added the kilogram per hour as well. And also when I wrote the heat capacity value here, I added the units, which was kilojoule per kilogram Kelvin. And the Kelvin is also attached to the temperature value here. So we can see that the units will start cancelling each other. So the Kelvin that is attached to the temperature will cancel the Kelvin that is attached to the heat capacity value. And also the kilogram that is attached to the mass flow rate will cancel the kilogram that is attached to the specific heat capacity. So at the end, we are going to get 873180 kilojoule per hour. This is what we are going to obtain. And mind you, we have to have our final value in a form of kilojoule per second. So when you have any value and then you want to divide it, or like you want to convert it to kilojoule per second, just divide it by 3,600. So when we multiply the whole of these by kilojoule per 3,600 seconds, we are going to get 242.5 kilojoule per second. And 1 kilojoule per second is the same as 1 kilowatt. And hence, our heat required will be equal to 242.5 kilowatts. So this is how the calculation should be performed. Anytime you get similar question like this, anytime you get similar question, the first thing is that find out whether you are having sensible heat at work or you're having latent heat at work. And after that, start fishing out the parameters from the question. So after fishing them out, fix them into the formula and then perform the calculation. Do not forget that you should have your final answer in a unit of kilojoule per second. So when the question comes in such a way that the flow rate is in kilogram per hour, then try and do the conversion. And you can do the conversion by just dividing the flow rate by 3,600 seconds. So that is how basically we do it. Now let's move on to this particular trial question. I am not going to solve this question. So please read this question well, pause the video, solve the question, and then comment with your answer. I will also check it for you. Thank you very much.